Welcome to another day of Math 8. Today we'll be working in Unit 1, Lesson 14. We're going to learn about alternate interior angles. To learn about alternate interior angles, we are going to use some of the previous learning that we've already used to make some predictions, to make some claims, and then we're going to use rigid motion to back up our claims as evidence. To get started, we're going to explore what our goal is today is we're going to explore why some angles are always equal. If we're saying some angles are always equal, that means that some angles are not always equal, and we'll talk about what that means here in a few minutes. To get started, we have this diagram here of two lines that are intersecting. When two lines intersect, we always get four angles, and there's going to be, of those four angles, two of them will always be equal to each other, while the other two are always equal to each other. In order to find these, we have to apply a couple of things from our past. First off, we understand that this angle is 30 degrees, but as we keep coming around all the way to this line, we're supposed to find angle JGH. We know that that angle combined with the angle next to it makes a straight angle. As a straight angle, we know that that straight angle must add up to 180 degrees. So this becomes a small mystery of what number is this, or what's missing from this angle. We can quickly find that by taking 180 degrees and subtracting the 30 degrees from it, and learn that angle JGH is 150 degrees. Now when we move on to this next one, find and label a second 30-degree angle in the diagram, we can think back to our understanding of vertical angles. And we know that a vertical angle, set of vertical angles, are two angles that share a common vertex and they're opposite of each other in an intersection. We also know that a rotation of 180 degrees proves they're congruent. So if I were to rotate this angle, JGF, 180 degrees around point G, it would map exactly onto HGI to make 30 degrees. By that same logic, we can know that the vertical angle to the one we found, JGH, must be angle FGI, and so that angle must equal 150 degrees. Again, using principles of what we call supplementary angles, or two angles that add together to equal 180 degrees, and vertical angles with the understanding that vertical angles are always congruent, we can determine unknown angle measures. So when we talked earlier why some angles are always equal, vertical angles are always equal because of a rotation of 180 degrees around a center point. Great. Now what happens when we take a set of parallel lines and run another line through it? Well, what happens is we actually get a new line right here, or a third line, that's not parallel to the other lines, but it has a special job. We call this line a transversal. And a transversal is a line that intersects two or more lines at exactly one point. So this line HJ intersects exactly once here on line DF and only once here on line AC. And by causing that intersection of lines AC and lines DF, we have 8 angles that are created. One of the angles that's given to us here is angle ABE, which is 63 degrees. We can actually use that on parallel lines to help us find the other angles that are around. Quickly using the principles that we just talked about a moment ago, if I recall the piece about supplementary angles, I take the angle that's just adjacent on this 180 degree angle. To help me see it, I'm going to go like this and look at just the 180 degrees. And I see that 63 degrees plus what is 180 degrees? I can find that by some subtraction. 180 degrees minus 63 should equal 117 degrees. So we've already found one angle. We're going to go ahead and remove this, and we're going to talk about how to find the other two. When we know that vertical angles are always congruent. So the given angle of 63 degrees is vertical to angle JBC. So we know this one must be 63 degrees. And we know that angle CBE is not only vertical to the one we found, it is also a supplement to the given angle. So remember, a supplement or supplementary angles is two angles, exactly two angles that add together to have a sum of 180 degrees. So now the question is, how do I find these other four? If you just made a prediction and said, well, these other four angles look a lot like these four angles, you would be right. The key thing that we have to remember here is that AC and DF are parallel. That's a big deal when a set of parallel lines are cut by transversal. What we know is when parallel lines are cut by a transversal is that this set of angles are exactly the same as these angles. But we have a new vocabulary term to help us know exactly how to describe the relationships here. The vocabulary term that we're going to use is alternate interior angles. As we talk about alternate interior, let's break down what that means. When we say interior, we're talking about this section right here between the two parallel lines. Wow, interior. Oh my goodness. Let's go with interior. And what we mean by interior is we are inside or in between the lines. Now, when we talk about alternate, we're talking about moving from one side of the transversal to the other side of the transversal and to the next interior point. So remember, alternate comes across the transversal. Interior means we're inside of these two boundary lines. And what we know under parallel lines is that this angle right here that is alternate interior of parallel lines is going to be 63 degrees. Now, right now I'm making a claim and I'm not giving you any evidence, but I'm going to show that evidence to you in a moment when we talk about congruent angles. And if you remember about congruence, we proved congruence with rigid transformations. By finding just this one angle, I can now find the other angles here by the same principle. This 117 degrees is also alternate interior to angle DEB. And then the vertical angles will also be congruent to what we just found. Okay, so what do you notice about the angles with vertex B and the angles of vertex E? Well, we should notice that they are equal in measure, and we can actually see that when we take our little patty paper here, and if we take the intersection through vertex B, or through point B, and we translate that intersection straight up to the other intersection, we see that we have the exact same relationship going on between both angles. We see that the angles down here around what was given, 63 degrees, 117 degrees, and so on and so forth. When we translate along from B to E, from one parallel line to another, we see that the same exact angle measures exist in the other intersection. This only happens when these two lines are parallel and a transversal cuts and makes new angles. So let's go ahead and practice a little bit more of this. We have another set of parallel lines, DF and AC, that is being intersected by transversal HG. And it's just called HG because those are the furthest 2 points. What we know about these intersections is we know that we don't know these angles, but we do know angle GEF is 34 degrees. Our task is to determine what these other angle measures are. What we just talked about earlier was that a translation from one intersection to the other along, or when there's parallel lines. So the translation along the transversal from one parallel line to the next will give us angles that are equal in measure. So there's a translation. I'm going to prove why alternate interior angles are also congruent here in a minute. But for right now, we can see that these two angles that are corresponding, they're in the same spot, are 34 degrees. That's really important for us because we know that this angle is a vertical angle, so it's 34 degrees. And this angle here is an alternate interior angle, again, inside of the two parallel lines. Alternate sides of the line must be 34 degrees because we have parallel lines. When we know that this alternate interior angle, I'm going to go like this, draw a little arrow, and these two are alternate interior. There we go, writing interior again, are interior angles. So we would say that angle DEB and angle EBC are alternate interior angles. And now we can apply our principles that we talked about earlier with supplementary angles. These two angles have to add up to 180 degrees. So 180 degrees minus 34 degrees will give us 146 degrees. And then we can just use our principles of vertical angles, 146 degrees here, 34 degrees here, to complete our task and know what both of those angle measures are. Let's look at here one more example, again with line DF and AC. What do you notice about the angles in this diagram as compared to the earlier ones? How are the two diagrams different? Well, I noticed that up here in this intersection around point E, they gave me this angle measure of 108 degrees. And down here, they gave me an angle measure of 63 degrees, whereas on the last two, they only gave me one angle measure. So I'm a little bit suspicious that something is going on here. What I noticed about the two diagrams as well, though, is these two lines, they don't quite look parallel. When I look at just line AC and DF, something seems kind of different here. I'm going to set my pens on here. And I want you to see if you notice what's going on. If you said that the lines are no longer parallel, you'd be right. And let's look and see what happens here. When I take this straight angle right here, angle FEH and angle HED, and I find out what the measure of angle HED is, subtract 108 from 180, I get 72 degrees. I can also find that same measurement vertically here to 72 degrees. But here's the problem. You see these alternate interior angles right here? They're not equal. And why is that? Well, remember that we talked about that translation from one intersection to another. I'm going to go ahead and intersect or translate from this first intersection where we worked on it. I'm going to translate down to the other intersection. And what we see is that my angles are not equal anymore. Because the lines are not parallel, we've lost that congruent relationship that was created by parallel lines when the transversal came through the other two lines. So sometimes these angle measures have congruence with the related angles. Other times there is no congruence when the parallel lines or when the parallel relationship no longer exists. So all we have left to work with here is our concepts of supplementary angles and vertical angles. So we know this is 108 degrees. We'll have to find out the measure of angle B by taking 180 degrees and subtracting 63 degrees from it, and finding that that is 117 degrees. And then by vertical angles, we know this other angle ABJ is 117 degrees. And by vertical angles, we know the angle JVC is 63 degrees. Alrighty. Let's get to the evidence part. I made a claim that alternate interior angles are congruent. And I just made that claim. I put that out there. I showed you that I can translate from one line to another. But when we talk about alternate interior angles, we have to talk about a different kind of transformation. We have to talk about how lines L and K are parallel. That right there is super important. So we have to know that lines are parallel before we even get going on with anything else. But we see something is different here is that they told us M is the midpoint of segment PQ. So let's use that and come to a new understanding about why or how we can claim that alternate interior angles are congruent. So this is our claim. Let's get some evidence. When we think about these angles, let's go ahead and get everything on here, because we're going to use our midpoint, and we're going to use what we've been working with on midpoint for the last couple days, and that was rotation. We know that rigid transformations prove congruence, because under a rigid transformation, we know that angle measures are kept the same, or they must be equal, and we know that lengths of segments must be equal. So we're going to compare these angles. We're going to look at this interior angle right here and this interior angle right here. And under a rotation around midpoint M, 180 degrees, watch what happens. We see that those alternate interior angles are exactly the same. Now, just to show you that there's no magic here going on, I'm going to call this one angle 1, and I'm going to call this one angle 2. And I'm going to do the exact same thing that I did a moment ago, 180 degree rotation. You'll watch and see that angle 1 and angle 2 are interchangeable, or they're congruent under a rotation of 180 degrees around the midpoint. This is how we can claim, or how we can prove that our claim of alternate interior angles are congruent is true. We say that a rigid transformation, we would say a rotation of 180 degrees around midpoint M maps alternate interior angles. There's some other cool relationships we're going to find with that as well, but not in today's lesson. Let's take that same principle and let's see if it will work for two lines that are no longer parallel. So we've changed the game just a little bit. The lines are no longer parallel, but midpoint M is still the midpoint that's here. Let's see what happens. So we'll go ahead and take the line PQ, or transversal T here, and line L, and line K. Oops, that's not a very good job. And let's do a 180 degree rotation. I'm going to call this angle 1 and angle 2 around midpoint M. Here we go. So we rotate 180 degrees. We see points P and Q change places, but we also see something else. Let's see that again. But this time I'm going to do this with labels. So here's line L, here's line K, and here's transversal T. I'll put point Q here, I'll put point P here, so you can see that they're trading spots and point M remains. So here we go again, 180 degrees around midpoint M. changing places of the segment. So P is in place of Q, and P is in place of Q, Q is in place of P. And we see that angle 1 is actually much smaller than angle 2. And our argument from earlier that alternate interior angles are always congruent, that's not true. They're still alternate interior angles, but they're only congruent when the lines are parallel. And we know that that is true because of our evidence of rigid motion or rigid transformation. So to recap, here's a couple things to remember. When two lines intersect, we have a bunch of things that happen. First off, when two lines intersect, we end up with vertical angles that are equal, adjacent angles that are supplementary, means they add up to 180 degrees, and we can find those angle measures fairly easily. We know that when two parallel lines are cut by another transversal, let's talk about that for a minute. Two parallel lines cut by a transversal, we end up with two pairs of alternate interior angles, and we know that those alternate interior angles are congruent only when the lines are parallel. Alternate interior angles are equal in their measure because a 180 degree rotation around their midpoint takes one angle, or takes their vertices, these two vertices, and changes them to their place. So angle 6 would rotate directly to angle 4. Angle 5 would rotate directly to angle 3. We know that this rotation proves congruence because it's a rigid motion. Using what we know about vertical angles, adjacent angles, and alternate interior angles, we can find the measurements of any 8 angles that have been created by a transversal that comes through any two parallel lines. There's one thing to always remember though, and that's here at the bottom. When lines are not parallel, so when lines, I'm going to say cut by a transversal, are not parallel, alternate interior angles are not congruent. But when the two lines are parallel, alternate interior angles are congruent. So parallel lines, we see congruence. Non-parallel lines, we don't see that. But again, keep in mind, vertical angles, even when the lines aren't parallel, vertical angles still remain congruent to each other, and supplementary angles still add up to 180 degrees. That is the end of the lesson for today. Thanks for hanging in with me for so long. You're doing a great job. Please, as always, send me questions if you're not understanding the lesson. Watch the lesson as many times as you want. Make sure that you believe in yourself, and don't you dare give up. Have a great day.